So this time in lab, we're going to be talking about how to interface a keypad to the Arduino microcontroller. Now, this lab has an awful lot of ground to cover. It's 9 pages long. There's no formal pre-lab, but you need to really understand the material before you arrive at lab. So the first thing we're going to do is understand how the matrix keypad works. You can see here a picture of a matrix keypad on the left. You see that there are 12 keys. This is a 3x4. We could also have one that would be 4x4 or even larger. But in this case, with 12 keys, you could imagine that we would need to have 12 different switches, and that is true. If we were to do this the way that we have done other switches or other push buttons, we would need to have 24 different wires coming out, one for each side of each of the switches. But that would really be prohibitive. 24 wires to interface to the microcontroller, even 12 wires would be really prohibitive. That would use every single pin that we have accessible to us. So instead, what we're going to do is we're going to think of this as a matrix. And over here on the right, you can see this is how the inside of the switch actually works. So each one of those push buttons. So here's push button number 1. Push button number 1, when it's pressed, will make a connection between row number 1 and column number 1, between the top row and the leftmost column. And so that's all it does, is that it makes a connection. If I were to press button number 8, it would connect between row number 3 and column number 2, between the third row and the middle column. If I were to push the hashtag button, it would connect row 4 to column 3. That's really all that the inside of the switch does. We're going to need to interface to it in a more sophisticated way to be able to allow it to do complicated tasks. So what we're going to do is we're going to send a special signal over each one of the columns one at a time. So let me flash back up to here. If I send a special signal over column 1 and then I detect it coming out of row number 2, the only way that that could happen is if button 4 was being pressed. And if I send a special signal over column 3 and I receive it over row number 4, then I know that the hashtag button must be pressed. And that's really what we're going to do. We're going to send a special signal over column 1, check all the rows. Special signal over column 2, check all the rows. Special signal over column 3, check all the rows. And then we're going to repeat that, waiting until eventually one of the buttons is pressed. So in our case, we're going to send a high signal over 2 of the columns. High is going to be the boring or uninteresting standard case, and the low signal, a binary 0 or 0 volts, is going to be the special case. That's the designated column that we're currently trying to check. We'll then check each of the 4 rows to see whether any of them are sensing that unique low signal that's only being sent out over one column, and if any of the rows are low, then we'll know that the button in that column and that row has to be pressed. So here's the summary. We send a 0 on the left column, sending a 1 on the other 2 columns. Is the top row equal to 0? If so, button number 1 is being pressed. Is the second row equal to 0? If so, button number 4 is being pressed. Is the third row equal to 0? If so, button number 7 is being pressed. Is the bottom row equal to 0? If so, then the asterisk button is being pressed. Then we repeat that for the middle column, and we repeat that for the right-hand column. And that's the process that we're going to use to check each of the 12 keys. Now, if it turns out that none of those statements succeed, then that means that no key is being pressed. And the vast majority of the time, no key is going to be pressed. We're going to constantly be checking to see whether a key is pressed, and it won't be. So then we're going to have to go back and check again. So we'll just repeat saying, oh, no key was pressed that time. This is the idea of how the keypad works. We're going to connect the keypad, and I'll show you just the picture here I think is more useful. You're going to use the same breadboard that you used when we were talking about looping in microcontrollers. It'll have this bar LED over here on the far left-hand side. You're going to plug the keypad over here on the far right-hand side. You'll notice that this is all the way as far right as it can get. And we're going to use a ribbon connector, a ribbon cable. And you can see that the ribbon cable is connecting these 7 pins to the 7 pins over here on the microcontroller. When you do that, 2 things to keep an eye on. Don't twist the ribbon cable. You'll notice that yellow's on the left here and yellow's on the left here. That means that I didn't twist the ribbon cable. The other thing is you're going to be really tempted to pull these apart. I would just ask you, please don't pull them apart, because eventually you'll pull them all the way apart and then they won't be a ribbon cable anymore. They'll just be individual cables. So you can see here there are 7 pins for the keypad and 7 pins for the ribbon connector, and that's going to be the connections that we're going to use. You're also going to need to connect the grounds of the 2 boards, and then 4 wires are going to go from the microcontroller to the tops of the bar LED. Notice that the resistors are already here to limit the current, and they're going to ground, but these 4 wires are going to go to the bar LED. And then the last piece of hardware you're going to need to connect is this little piezo buzzer right here. And that's simply one side is going to go to ground and the other side is going to go to the last remaining general purpose pin, the pin 13. That's the last I/O pin that we have. That's all the hardware we're going to have for today. The keypad, the bar LED, and then the piezo buzzer, which you won't really use until the very end. The basic mode of programming the microcontroller, we have this block of hashtag defines. So here's where we're defining each of the rows, which pen each row is connected to, which pen each column is connected to, and which pen each of the 4 LEDs are connected to. And if you hook up the hardware like it was shown in the previous section, then these are the correct pen numbers for each one of those signals. That'll all be before the setup function. Then in setup, you need to set the columns to be outputs, and of course the LEDs are also going to be outputs, and then the rows are going to be inputs. But they're a special type of inputs. They're inputs with pull-up resistors. So you can see this says input pull-up. And what that does is it attaches an internal pull-up resistor that ensures that if no signal is, or if no connection is being applied to this, it will pull it up to 5 volts. It will default to be 1. Remember that the special signal we're looking for is the 0. So if it doesn't have any signal, we want it to default to being 1. And that's what input pull-up does. We're going to create this function called find key, and find key is going to have the opportunity to send out the special low signal. Here I've done the full first column, so I send out the low signal on column 1, send out the boring old high signals in columns 2 and 3, and then I'm going to check each of the rows. And here you can see that if it's on row 1, that's a 1. Row 2 is a 4. Row 3 is a 7. Row 4, I give it a code of 10, and we're using 10 to represent the asterisk. Now you're going to need to create a block of code just like this for the middle column, and that'll go here, and a block of code just like this for the right-hand column, and that'll go here, and just use the 11 to represent the hashtag. Now if it turns out that one of these buttons is pressed, then as soon as it gets this return, it's going to return back to the main loop, and it's going to return the number that appears after the word return. But if it doesn't return a 1 or a 4 or a 7 or a 10 or a 2, a 5, an 8 or a 0 for the middle column, or a 3, 6, 9 or 11 for the right-hand column, if it doesn't return any of those, then we know that no key is being pressed. And we're going to use 999 to be the code that indicates that no key has been pressed. It's just a code that I chose to represent that there is no key being pressed. So that's the return functions ensure that if any key is being pressed, we'll never get to the end. And if we don't get to the end, then we don't return a 999. Now, in the main program, there's a couple of things we need to do. Define an integer variable called key pressed. And then we're going to need to call the find key function. So we'll say key pressed, that's our integer variable, is equal to find key. That's the function that we just wrote. So we're going to call find key, and whatever it returns, we're going to put that into key pressed. So key pressed now contains a number, which is either a number 0 through 11, or it's the number 999. We're going to say, hey, if it's not 999, so exclamation point equal says is not equal to 999, then I know that a key has been pressed. And what I want to do is I want to output the least significant bit of key pressed. So I'm going to AND, so this is a binary AND, a bitwise binary AND of key pressed, that's our number, with a least significant bit. And that's the one that I want to send to the first LED. And then I want to send the second bit. So this is a binary that has a binary 2. I want to send that one to the second LED. Binary 4, send that one to the third LED. Binary 8, send that to the fourth LED. You don't need to stress out about the details of these commands. Just know that what this does is it breaks the number key pressed into 4 bits, and it sends each one of them to the corresponding LED. But it only does that if a key has been pressed. So in the intermediate mode, I'll just mention that the thing we're going to do here is we're going to allow it to display the number to the serial monitor, as well as displaying it on the LEDs. And there's a little trick here that happens, and I ask you to sort of identify what that trick is, what's the weird behavior, and how could you avoid it. And then we'll talk in detail about how to avoid that undesirable behavior. And then in advanced mode, now we're going to keep track of the last 5 numbers that have been pressed. And we're going to check and see whether the last 5 numbers that have been pressed are the correct, quote-unquote, correct code, 1, 2, 3, 4, 5. And if it is the correct code, then we're going to beep a couple of times. So I need to set up the beeper, the piezo buzzer. And then I'm going to create a new function here called check code. I'm I'm going to check to see if the code is the correct code. We'll also have a new function here called update code, which is going to shift each one of the numbers down by 1, so that the one that was the most recent now becomes the second most recent. What was the second most recent becomes the third most recent. In the same way that this year you're freshmen, but next year you'll be sophomores, and then the year after that juniors, and then seniors. This is sort of like allowing each one of the bits, each one of the numbers to move ahead by 1, and then the new number comes in the slot that's corresponded to the most recent number. Main loop, well, now in addition to receiving the key, now we're going to output the code. We're going to output it both to the LEDs and to the screen. We're going to update the code, keeping track of the most recent 5 numbers. We're going to check to see, is the code the correct value? If so, we beep, delay, beep. So it's kind of like a little beep, beep, and that keeps track of when the correct code has been entered. So a lot of changes that happen in this one. This is the end of the official lab, but if you'd like to earn a little bit of extra credit and you have a little bit of time left, you can then make it so that the first 5 keys pressed after the program begins are going to be recorded as the quote-unquote correct code. So it doesn't have to be 1, 2, 3, 4, 5. And it gives you some hints of how to do this. That would be strictly extra credit and only if you have time left. I don't think there's going to be a lot of time left, but if you do, I would encourage you to go ahead and try the extra credit. If you complete the extra credit, you will have done what I did as my junior year project in 1990. I did this exact project for junior year. I had 2 full weeks to do it, and you will have done it in less than an hour.